Okay, guys, so back, let's see. I said what I would do during the first part of this time was to discuss a little bit about the group project first submission. Okay, so you have about 18 days, so almost 3 weeks. Hopefully this is not the first you've started on this assignment. Hopefully you've already begun talking about it and begun thinking about it with your group. But in case you haven't, now would be a great time to start. Right? But one of the things that I wanted to point out is that, again, the third normal form is what we are looking for in this first part of this assignment. Right? So you will create or research a set of source data. Now, when I say create a set of at least 30 data items, I don't mean 30 cells in an Excel spreadsheet, okay, because that would be very small. Okay, I mean 30 columns. Okay, so you need to have, like, in a student database for a school, you know, your name would be a column, your surname would be a column, your email address would be a column, right? So you need at least 30 of those columns. I am not giving a limit, a minimum number of rows, because if I do that, then it may not be right for your group. Okay, you need to have a set of rows that you think is enough for you to be able to adequately analyze the data set. Okay, I can guarantee you one row, probably not enough. Okay, but no, one row is just not enough. Like, it's just not going to work. Okay, but there is no minimum number of rows that you need to provide. You do need to provide at least 30 columns. Now, that doesn't mean that 30 columns will show up in your normalized database tables. Most likely you'll end up with more as you begin the process of normalization. If you look back at our staff branch example, so the staff branch table had a certain set of number of columns, but then the staff table had only one column less. It was the branch address. But then the branch table had 2 columns. So we actually ended up with more columns total between our 2 tables. But again, the benefit through the lack of data redundancy, when you start talking about things like thousands or millions of rows from your source data, the storage space that's lessened overall becomes a bit less. Right, and so even though there are more columns overall, the benefit outweighs that problem. Okay, it's not really a problem, but you know. So you'll want to start with what we call an unnormalized data set. We will look at an example of that, not today, but we will look at an example of that, of what an unnormalized database looks like, an unnormalized table, right? You can put that into any schema of your choosing. You can use MySQL. It's nice, it's free. If you have access, that's perfectly acceptable. Others that you might have access to as well are okay. Every year I get some group asking me if they can use a NoSQL database. Absolutely, that's okay. You will need to show the equivalent requirements for a NoSQL database. All right, let's see. So then you will use the normalization process that we will discuss in class to create an ER diagram. So you'll need to produce an ER diagram. All right. You'll also want to create the necessary tables. You'll have to show how to create those tables using SQL. So we talked about that a few weeks ago, using the data definition language of SQL. And then you will also need to populate these tables, meaning you need to put the data from your unnormalized form into your third normal form tables. That will require SQL also, the DML, the data manipulation language for SQL. Okay, so the things that I need to see, there's 4 items that I'll need to see that I'll be grading you on. One is the UNF data, so an unnormalized set of data, basically one single Excel spreadsheet, all right, data in a grid or a spreadsheet. I'll need to see your ER diagram of your 3NF database that includes the participation and cardinality information, such as, 0 dot dot star on one side, 1 dot dot 1, or just 1 on the other side, and how those relationships are defined. Okay. So not just an entity, another entity, and a line between them. Okay, I need to know, what does that line mean? What is there a one-to-many relationship there? Is it a many-to-many relationship there? What type of relationship is that? Okay. I need to see the SQL for creating the tables themselves and inserting data from the UNF database table into the tables that you create. I showed you how you could use, if you use MySQL, you could use that user interface to create a table. It would generate the SQL for you. You are perfectly free to take that query, copy that query into a report or into a text document, and that will be your SQL query. Okay. So a view to recreate the original data set. So you're going to have one table. That's your unnormalized form. I need you to create a view that takes the data from your 3NF tables and basically recreates the grid of your unnormalized form. You will use that to prove that there's a slide back that talks about the lossless join property. We need to be able to see that all of the data from the original data set, from the unnormalized set that you took, all of that data is still in our database, just in a different form. It's in the third normal form now. Okay. Some different ways that you can submit this. You can submit all items as a report in a Word or PDF. Lots of students have done this in the past. Many of them have done this. Basically what they've done is they've submitted a report like this. You will be giving a final report at the end of the semester as well. So lots of the students basically took their existing report from their first submission, modified it, updated it according to the request from the customer, and then basically just submitted the same report again, but updated and modified it. You will not submit the same report again. You should not submit the same report again. Alternatively, you can submit them as separate items. Let's see. The assignment submission function on Microsoft Teams allows you to upload more than one attachment to a submission. So you could submit item 1 as an Excel spreadsheet or a link to a Google form. Sorry, not a Google form, a Google sheet. Item 2 needs to be a diagram. There are diagram tools. I'll show you one of those either tomorrow or next week, called diagrams.net. Used to be called draw.io. You could also use PowerPoint to draw a diagram. Items 3 and 4 need to be SQL queries. Okay, so you need to have a set of SQL queries that show how to create the tables and insert data. You need to have and actually create tables, insert data, and get rid of the columns that from the previous table that you no longer need. I'll modify this explanation to say that. Item 4 should be a view query. A query that creates a view that represents the linking of all the 3NF tables together. Okay. Okay. Back to this. All right. Are there any questions or comments? Let me pull that back up. Are there any questions or comments before we move on back to functional dependencies? Oh, one thing I do want to say too, I realize now, when I said that your final report will not be the same as this, that's because every group, you're going to submit an initial report or an initial submission here. May 20th is the deadline for that. No, May 30th, April 30th. Did I say May? No, April 30th is the deadline for that. I put it the Sunday before the midterm exams so that you wouldn't be dealing with this project over the midterm period. So there's that. But every single one of you, your group, the customer will review your design. We will grade you. I am the customer. I will grade you on your initial design for how well it adhered to the requirements that that you put out. Then for every single group, the customer will have a list of requests. Okay, they're going to want to see certain things in the final submission. Okay, your grade, your final overall grade will be dependent on how well you satisfy those requirements. Or if the requirement is not possible, or if the requirement is not something you can do, that your team can do, then you need to tell the customer why that can't be done. Okay? All right. Customers generally do not like being told no, but sometimes customers ask for things that are just not feasible, that are just not possible. Okay, and so if you, for whatever reason, believe that a certain requirement cannot be completed, then you need to tell the customer why it was not able to be completed. And it can't be something like, well, we just didn't want to. All right, customers don't really respond well to things like that. Okay, all right. So if there aren't any other questions, let's move on. Okay, there's another thing we'll talk about. We'll talk about full functional dependencies here. Okay, so the idea of a full functional dependency means that A determines B, or as we said before, B is functionally dependent on A, and B is not dependent on any subset of A. So let's say, for example, this is dependent on our understanding that sometimes the left side of a dependency might be more than one column. So for example, if I had your student number, let's see, I started writing something and didn't mean to write that. Okay, if I had on the left side, if I had your student ID, okay, student ID, this looks like student IP, but student ID, and the combination of your student ID with your name, okay, does that determine your surname? You're right. If I have your student ID and your name, I can figure out your surname from that. But did I need both of these pieces of information? No. What did I not need? Or what did I? Yeah. Student ID was plenty. If I had your student ID, that's all I really needed to determine your surname, right? So we would say that surname is functionally dependent on student ID and name, but it's not fully functionally dependent on student ID and name. It's fully functionally dependent on student ID alone. So if we were to write it like this, student ID determines surname. Okay, now we've got a full functional dependency because surname is dependent on student ID and not on any subset of that. You can say that if you have a functional dependency defined and the left side is only one column, you have a full functional dependency because it's not possible to be dependent on a subset if there's only one column on the left-hand side. An example here, very similar to the one I just gave. Staff number and staff name together determine branch number, right? Each value of the combination of staff number and staff name is associated with a single value of branch number, right? But it's only dependent on staff number, really, right? So what we would call this is we would call this a partial dependency. Okay. A full functional dependency is where this is determined by or dependent on this here, but it's also dependent on a subset. Okay. A full functional dependency is where this right here, there is no subset in this relationship. Okay. All right. Okay. So some characteristics that we need to understand, right? There's a one-to-one relationship, left side to those of the right side. In other words, if I know the left side value, if we have something, if we have a functional dependency, A determines B, right? If I know A, then I must know B. It doesn't have to work the other way. The example from before about where SL21, the staff number, determines the position manager. There's only one value for SL21 for position. They don't have, SL21 doesn't have multiple positions. They're a manager, period. The other way doesn't always work. Position can have multiple values, right? A manager could be SL21, could be some other person as well, right? So if we have a dependency like this, then this value represents only one value possible on this side. Holds for all time. Now that does not mean, when it says holds for all time, it doesn't mean that like, oh, our employee can never be promoted to a higher position. That's not what it's saying. What it's saying is that their staff number will always determine their position, right? So for example, the one we had before where name, the staff name determined the staff number in the current data we were looking at, but we don't know if that's true for all time because there may be future people who are hired who have the same name. Right. Okay. But the staff number will always determine the staff name. The name could change if they get married or divorced or something like that. All right. That name could change, but it will always be that way. That's going to be a one-way determinant. Okay. The determinant needs to have the minimal number of attributes necessary to maintain the dependency. All right. So we don't want to add in extra attributes unnecessarily. We clear on full functional dependency. So if I have multiple columns on the left when I don't need them, that's called a partial dependency. If I have only one column on the left, we know that's a full functional dependency. If all the columns on the left are necessary in order to have the dependency hold true, then that's called a full functional dependency. Okay. All right. There's another type of dependency that we need to talk about too that's related to our normalization process to get to what's called the third normal form, and it's called a transitive dependency. The idea being that if A determines B and B determines C, then we can say that C is transitively dependent on A. Okay. This requires that A is not functionally dependent on either B or C itself, but basically the idea is if A determines B and B determines C, then yeah, A determines C. So for example, if I said, if I had a table that was, that included things like your name, your student ID. Wait. Let's not do it that way. In this, I have to erase. Okay. Let's say for courses. Okay. Let's say we had a course ID, a course title. Okay, what else? An instructor ID. So instructor. All right, and a instructor name. Okay. And we assume that a course can have only one instructor in this example. Not always the case, but we'll say for this example, a course has one instructor. Okay. Then we could say that the course ID determines the instructor ID, right? Instructor ID. So a course ID determines the instructor ID. If I know the course ID, I know the instructor ID of who's teaching it, right? But instructor ID itself determines the instructor name, right? So we have a transitive dependency. Does the course ID, in this case, does the course ID determine the instructor name? Course can have only one instructor, right? Yeah, but it's what we call transitively dependent on course ID, which means it's not really that instructor name is dependent on course ID, is it? It's really more accurate to say that instructor name is dependent on instructor ID, and that the instructor ID is what's dependent on course ID. Okay, so this is what we call a transitive dependency. These are very important, okay, because we'll get to, let's look at an example here real quick. Back from slide 8 again. Staff number determines basically every other column in the relation of the staff branch relation. But branch number determines branch address. So we have a transitive dependency where staff number determines branch address, but it's really that staff number determines branch number and branch number determines branch address. Okay. Okay. That's gonna bring us to those two topics. Those two topics are what's really important for us to understand for bringing any unnormalized data set to the third normal form. So I need to make sure before we step into the next slide, I need to make sure you guys understand full functional dependency and transitive dependency. So now is the time to ask any questions or express any concern that you're not quite clear, because this is what we call the point of no return. Okay. right, so process of normalization. So it's a systematic process for taking an unnormalized data set through a series of steps, and with each step corresponding to a particular normal form. Okay, so the unnormalized data set basically has no rules on it. It's just our data in a grid type format, but each successive normal form, the first normal form, the second normal form, the third normal form, will all have specific properties that they must have. Okay. All right. So the first thing we're going to do is we're going to identify all of the functional dependencies in our data set. Okay. Yeah. So we're going to identify the functional dependencies. Once we do that, we're going to see that some functional dependencies might be partial. We're going to want to get rid of those. We are going to see that some functional dependencies might be transitive. We're going to also want to get rid of those. Okay. All right. So after we identify the functional dependencies, right? I just realized there's one thing I need to do. I forgot to set this up before. Let me do one thing and then I will come right back. There it is. Okay, that should be good. Okay. All right. So if we look at slide 8, staff branch relation again, if we identify all of the functional dependencies for our staff branch relation, right, we can say that staff number determines staff name, determines position, determines salary, determines branch number, determines branch address. Okay. We could also say the branch number determines branch address. We could also say based upon the data that we have, branch address determines branch number. We could also say things like the branch number and the position combination determines salary. And because the branch address and branch number are currently dual bidirectional dependencies here, then branch address and position together determines salary. Again, this is based on the current data as it exists. Now, what do you guys think are functional dependencies that are probably going to be true for all time? And let's just number them 1, 2, 3, 4, and 5. Okay. Let's not try to have you type all this out. Okay. So Kershot says 1, 2, and 4 are probably going to be true for all time. So you think 3 and 5 are probably not true for all time. I can agree with that. Okay. So yeah, I would say this one is probably not true for all time. Maybe, I mean, it's an address. It's not like multiple businesses can hold the same place. But this one is a better option for what we will call a primary key situation. Yeah. And then this one for the same reason. Yeah. And Metahan, you're thinking the exact same thing I am. This one right now, this is a good question mark, right? What if two people work at the same branch at the same position but have different salaries? Maybe two different salespeople, two different assistants, two different supervisors. Maybe it's a large branch and there's two supervisors, right? Obviously for managers, that's a single position, one manager at the branch. But yeah, two different people, same position, different salary is entirely possible, right? So yeah, so I would say this one is probably not a true for all time type of thing, most likely, right? Okay, so yeah, so these are the ones we're going to concern ourselves with mostly. This is a right? So this is a true for all time where staff number determines everything, branch number determines branch address, right? With the branch number, branch address one being what we called a transitive dependency, okay? Which basically, if you ever get a functional dependency where both parts of the functional dependency are inside of the right-hand side of another functional dependency, then you have a transitive dependency. Okay. All right. Let's look at an example set of data. Now let's assume that on this next slide, when we talk about this A, B, C, D, and E, right? Let's assume that what we see here is going to hold for all time, just as we start identifying the dependencies, okay? Okay, so let's assume that it's true, even though there's a relatively small amount of data. Okay, so let's look. All right, so let's identify some dependencies. Okay, so what dependencies do you see? And you can just use the column letters here. So capital A, B, C, D, and E column letters to determine your functional dependencies here. All right. So Bousse says A determines C. So if I have an A here, I get a Z or a Z if I'm speaking British English. E, I get an R. A, Z, E, R, A, Z. Yeah, okay. I can see that one. Right, good. Okay. So another one, B determines D. B. Okay. Before we go to that one, because I can't pull this down just yet, what about the reverse on C and A? Does it work both ways here? Yeah, so C and A kind of are a dual dependency here. Okay. We want to get all columns involved in a functional dependency in some way. So we either want them to be on the left side of functional dependency or the right side. It needs to be both ways. So here, this one, we would say this is A determines C. This one we would say C determines A. So we're still missing 3 columns. We need to get 3 more columns involved somehow. Does A determine B? No. Because A here is a B here, but A here is a D here, so that's not right. So Bousse suggests that B determines D. Let's see. So if the value here is B, which would be these two rows here, and that determines, that's W, yep. D results in W, yep. F results in S, yeah. Yep, that's a 1. All right, so here we would say B determines D. Yep. This one, you'll notice, does not go the other way. Isn't reversed. All right. Because if I have a W here, well, for these two, it becomes a B. Yeah, that works. But here, a W here does not give a B here. So therefore, B is not dependent on D. Column B is not dependent on column D. Okay. But we got to get one more column in here. E somehow. Does B determine E? Island, let's see. A B here gives me a Q, but a B here gives me a P. So nope. So just in the first two rows we know. Okay, Bousse, you're getting to the place I think that we're getting to, right? Where we're going to have to use 2 columns as our determinant, right? Because a Q here, there's no single column that I can say, I know what produces a Q over here, because A produces a Q, but E also produces a Q, right? So it's not that Q determines anything, and it's not that A here produces a Q here, produces a T here. That's not gonna work. BB, QP, nope. ZR, QP, nope. Sorry, ZQT, nope. WWQP. So yeah, single column doesn't work, right? But right, so the combination, let's see, Abdurrahman, sorry, Kurshad, you're saying BD. Oh, we've got conflicting responses there. One of you says AB and one of you says BD. Ooh. No one suggested that E determines anything. That's interesting. But that's because T, if we look at these 2 rows here, W and S, nope. Z and Z, okay, good, but R, no. Ugh. T and T, D and F, nope. A and E, nope. Okay, so E alone, not a determinant. But you guys are suggesting, one is suggesting the combination of A and B. And one of you is suggesting the combination of B and D. Ooh, let's see. Combination of B and D. B and W together produce Q. B and W together produce P. Oh, same combination here produces a different result. So B and D is not going to be our answer today, unfortunately. Okay. Let's see, Bousse, let's see about your response. A and B produces Q. E and B produces P. A and D produces T. E and D produces Q. A and F produces T. E and F. Oh, well, you notice, do you guys notice what I noticed? The combination of A and B, every row is unique, right? There is no duplicate row here for A and B. So yeah, of course that would produce a functional dependency there. So if we remove our last one there, yep, A and B generate E. And I'm going to draw it here, just like Bousse did. So these would be our functional dependencies for this. So now we've identified A determines C, C determines A, B determines D, A and B determine E. Also notice that because of this, because of these two here, we could have also said C and B determine E. Basically, C and A are interchangeable at this point. Okay. Right. So what the first thing that we're going to do is we're going to identify a primary key. Okay. So the first thing that we need to do with our relation is figure out what column or set of columns determines all other columns in the relation. Okay. So if we look at our branch relation, our staff branch relation, so what we'll do is we'll determine the primary key and then we'll end there for today and then come back and talk about normalization tomorrow. All right, so let's identify the primary key. So our determinants, if we look back at slide 22, I think is actually what we're looking for. Yeah. So if we look here, so for our staff branch relation, what column or combination of columns should be our primary key? What do you think? What column or set of columns, its value determines all other columns? Right. Staff number on its own determines all of our columns. Let me move on. Okay. You remember which slide we're on. Right, so staff number, right? These are for the 5 functional dependencies we looked at, the determinants, the things on the left, were staff number, branch address, the combination of branch number and position, the combination of branch address and position. We kind of determined that the ones, this one and this one and this one are really not good for all time, right? But we're going to say, let's identify which attribute or group of attributes uniquely identifies every row, every possible row in that relation, right? So any attributes that are not part of the candidate key should be functionally dependent on the key itself, right? So the only candidate key, and therefore the primary key for the staff branch relation, is staff number, as you guys have suggested. Great. So every other column is functionally dependent on that primary key staff number. Okay. What about the other one? Let's see. What about 5? What about this? Okay. What would be a good primary key here? Or if you want to see it in the other format, like this. This has all of our functional dependencies here already too. Right. Okay. Right. So A alone is not a primary key, right? Because A alone does not determine E. B alone does not determine E either. But the combination of A and B determine E. We could also say the combination of A and B determines C, because A determines C. B just becomes that extra piece of information. Kind of like when I said, if I had your student number and I had your name, could I determine your surname? Yeah, but I don't need your name. It's extra, right? So, so in the same way, if I have A and B together, I'll know all of the other columns because A determines C, B determines D, and the combination of the two determines E. Okay. So if we look at there, right? All right, so the determinants that we looked at in our example relation here, A, B, C, and the combination of A and B. The only determinant, although that functionally determines every other attribute, is the combination of A and B. Okay, so A and B would be our primary key. Again, because we had this A determines C and C determines A, we could also identify the combination of B and C as a primary key also. Okay, could have also been a primary key. If we don't choose it to be the primary key, it just simply remains a candidate key. All right, remember, we have two candidate keys, AB and BC. Which one we choose becomes the primary key. All others just remain a candidate key. So they still uniquely identify our rows, but they're just not the ones chosen to be a primary key. So what we'll get into tomorrow is the process of normalization, where we become more and more restricted, less vulnerable to update anomalies, fewer incidences of data redundancy as we make our relations stronger and stronger. Okay, if you want to see it visually, it'll look something like this. All right, where it's not listed, but the thing out here, what we call that the UNF database, the unnormalized form, right? Where we take something and take a unnormalized database and bring it into the first normal form. Then we bring it into the second and the third, and then voice cod, fourth, fifth, and other higher normal forms, right? Okay. Questions before we end for today? Or comments? Right. So when we end this set of lecture slides tomorrow, you should be able to pretty much have all the tools that you'll need for your first submission for your group project. Okay, the only thing you'll be lacking is your data set that you research and come up with. All right. Have a good afternoon, everyone. 3:14. We are ending at pie time. So it's 3:14. And I hope you guys have a good afternoon and see you tomorrow morning.